Hello students, good morning. Today we will discuss about the point force between two parallel current carrying wires. It means there are two wires of length L1 and L2. The wire first, this is the wire second. The length of wire first is L1 and length of, or we can say the current passing through this wire first is I1 and current passing through wire second is I2. These two wires are parallel to each other. Then these two wires exert a force on each other and they exert a force of attraction on each other. This is the force exerted on wire second due to wire first, and this is the force exerted on wire first due to wire second. And these two wires will attract to each other. These two wires will attract to each other. And if these two wires are parallel to each other, here also these two wires are parallel to each other. This is the current I1 and the current I2. In this case, the current is opposite direction. That is, current is anti-parallel. Here, current is parallel. Therefore, in this case, the force acting on this wire will be in this direction as this type. The force on the second wire due to first wire and force on the first wire due to second wire. These two forces are opposite to each other and will go away from each other. Therefore, these two forces will repel to each other, or these two wires will repel to each other, and there will be these two wires will repel to each other. There, in this case, currents are in the same direction. That is, the currents is parallel. Then two wires attracts to each other. And if current is anti-parallel, then two wires repel to each other. Then today we will discuss how this happens here. Now we will discuss about how this happens here. Two wires are taken of same length L. Suppose this is wire first of infinite length and this is wire second. This is wire first, this is wire second. These two wires are separated by distance d. The distance between two wires is d, and these two wires are parallel to each other. Then the current in the wire first is I1 and current in the wire second is I2. The current is in same direction. Two wires of length L are separated by distance d, and these two wires are parallel to each other. The current in first wire is I1 and current in second wire is I2. They are separated by the distance d. Now, we know that when a current is passed through a conductor, then magnetic field is developed around that conductor. Now, this is wire first. The current passing through wire first is I1. Due to this current, the magnetic field will produce around this wire. The magnetic field will produce around this wire, and the magnetic field due to the wire first or due to the current flowing in the wire first is developed, and in this magnetic field we have placed another wire, that is wire second. This wire second is placed in the magnetic field of wire first, and this magnetic field is due to the current I1, that is the current in the wire first. Now when we place a current carrying conductor in a magnetic field, then that conductor experiences a force. Here is a magnetic field. This magnetic field is developed due to this wire, and we have placed this wire second in the magnetic field produced by the current in the wire first. Then this wire second will be experiences a force. Now how this force will be experiences on this wire second, and what is the direction of force? And the direction of force can be find out by the right hand rule. Our direction of magnetic field also can be find out by the right hand thumb rule. This is the wire first, and the direction of current is in upward direction. Then right hand rule, that is held the conductor in a right hand in such way that the thumb is in the direction of current. Thumb is in the direction of current. Then curled fingers will indicate the direction of magnetic field. This is the conductor. Here is the magnetic field due to this conductor. This is the direction of current. Then the magnetic field here, the magnetic field will be inward direction, that is into the plane of paper. Therefore, we can say this is the magnetic field which is produced here, and this is inward direction. Now we have to find the force experienced by the wire second. Force experienced by the wire second, which is placed in the magnetic field produced due to the current in the wire first. Now we can apply the right hand rule here. Then the direction of magnetic field is inward. Then direction of current here shown, we can apply this right hand rule. Already we know, or we have already applied the right hand rule. This forefinger indicates the direction of current. This middle finger indicates the direction of magnetic field. Then this thumb will indicate the direction of force. Point this forefinger in the direction of current. This is the direction of current. Then this middle finger is pointed in the direction of magnetic field as this type. Then the force will pointed in the, or this thumb will indicate the direction of force. This thumb, that is, this is the direction of force. We can write here, this is the direction of force which is acting on the wire second. We can say this force as a F, that is force on the wire second. This force is due to the current in the wire first. Therefore, we can write here F21. Now, we can find the magnitude of this force. That is, the magnitude of force is given by the equation. We know that the force experienced by the conductor in a magnetic field is given by F is equal to I B L sin theta. Here I means the current. Which current? The current in the conductor which is placed in the magnetic field. Therefore, current in the second wire is I2. Therefore, we can say that the force is F21. Therefore, we can write here F21. Then current, that is the I2. That is current in the conductor. Then magnetic field B, and L is the length of conductor. And sin theta, here sin theta, theta is the 90 degree, because the direction of magnetic field is inward and the direction of force is perpendicular to the magnetic field. Therefore, we can say here sin 90. That is, we know that sin 90 is equal to 1. Therefore, F21 will be equal to I2BL, because sin 90 is equal to 1. Now, the magnetic field. In the last lecture, yesterday, we have already discussed the magnetic field. That is, a straight conductor we have taken and the point P is considered here. Then the current in the wire is I. Then the magnetic field produced at this point P is given by the equation, that is mu is V is equal to mu naught upon 2 pi I upon D. In last lecture, I upon R, where R is the distance appointed from the conductor. We can apply this formula here, and the magnetic field produced at this point due to the current in the first wire can be given by, therefore B is equal to mu naught upon 2 pi I upon, here R is the distance, that is here we have taken the distance D. Therefore, B is equal to mu naught upon 2 pi I upon D. We can put the value of magnetic field, and here current I is nothing but the current I1. The current I1, that is the current passing through the conductor first. Therefore, we can write here this I2 remains as same, and the magnitude of P is mu naught upon 2 pi I1 upon D into L will be as it is. Therefore, this is the force on the second wire due to the first current in the first wire, that is I2 mu naught upon 2 pi I1 upon D into L. If we take the force per unit length, that is force per unit length, you can write here force per unit length of wire. Therefore, we can write here F upon L. This will be equal to F upon L is equal to this mu naught upon 2 pi, this I1 into I2 upon D. This L will be taken on the left side, then this will become force per unit length of wire, that is F upon L is equal to mu naught upon 2 pi I1 I2 upon D. This is the force per unit length. Now we will consider the wire second. The current in the wire second is, say, equation 1 here. The current in wire second is I2. Therefore, this wire or this conductor, due to the current I2, will the magnetic field around this wire. Now, in the magnetic field of wire second, we have placed the wire first. In the magnetic field of wire second, we have placed the wire first. And the current in the wire first is I1. Then, we know that when the current carrying conductor is placed in the magnetic field, then it will indicate it will experiences a force, and that force can be given by as same like as this force. Now here is the magnetic field due to the current in the second wire. We can again apply the right hand thumb rule to find the direction of force. That is, this is the current in this direction. Right hand thumb rule can be applied here. Hold the conductor in the right hand. Point the thumb in the direction of current. Then the direction of magnetic field due to the wire current I2. Here is the magnetic field, and this magnetic field, this is the conductor second, that is wire second, and the magnetic field produced at point here will be outward direction. This is the outward direction of the magnetic field. That is, magnetic field produced at this point or near this wire second will be outward direction. Therefore, we can write here the symbol of this outward direction. This is the outward direction. Magnetic field at this point is outward direction. Now, the force experienced by this wire first in this magnetic field due to the current I2 is given by the equation F is equal to same equation I B L sin theta. I B L sin theta. Now, here current in the wire first. This current I is the conductor which is placed in the magnetic field. That is the current passing through the conductor which is placed in the magnetic field. And this current is nothing but the I1. Therefore, we can write here, and the force is F12. That is force experienced by the wire first due to wire second, and which is equal to IBL sin theta, and this current is I1, B is the magnetic field, L is the length of conductor, and here theta is 90 degree, and sin 90 is equal to 1. Therefore, we can write here F12 is equal to I1 BL. How can we find the direction of that force which is experienced by the wire? Again, apply the right hand rule on this wire. Here we can point the forefinger in the direction of current. This is the direction of current. Forefinger is pointed in the direction of current. Then this middle finger is pointed in the direction of magnetic field. Magnetic field is in outward direction. Then this thumb indicates the direction of force. Therefore, the direction of force is toward this wire. That is, this is the direction of force. And this force is the force acting on wire first due to wire second. Therefore, we say that F12. This is F21 and this is F12. This force is acted in this direction and this force is acted in this direction. That is F12 is equal to I1BL. magnetic field. The formula of magnetic field, which is discussed in last lecture, and here we have find out. Then we can write here the magnetic field which is produced around this wire will be mu naught upon 2 pi, and the current due to the wire second, therefore this will be equal to I2, and distance is remain same, that is the d. Therefore b is equal to mu naught upon 2 pi I2 upon d. Put the value of magnetic field here, therefore I1, then mu naught upon 2 pi, then I2 upon d into L. Then we can find out here again the force per unit length of wire. The force per unit length of wire, that is we can find out F upon L is equal to mu naught upon 2 pi, this I1 I2 upon d. This L will be taken in the left side, therefore F upon L is equal to mu naught upon 2 pi I1 I2 upon d. Say the equation second. That is from equation first and from equation second, we can say that the force per unit length on the both wire first and wire second is same. That is force acting on wire first due to the current in the wire second, and the force acting on wire second due to the current in the wire first is same in the magnitude, or we can say these two forces, this F21 and this F21 and the force F21 and force F12 are equal in magnitude. That is force per unit length is equal in magnitude, but the direction of force is opposite. Therefore, we can say that these two forces will attract to each other. That is, we can say that the similar or parallel currents, the parallel current produces a force of attraction. That is, from this equation we can say that F12 or F12 is equal to minus F21. Force on the wire first due to wire second is equal in magnitude. That is, force on the second wire is equal due to first wire F12 is equal to F21. But the direction of these two forces are opposite to each other. Therefore, here is the sign, negative sign is shown here. This negative sign indicates that the two forces are opposite to each other. That is, the force between two parallel current carrying wire. If the current is in the same direction, then these two wires attract to each other. These two wires will attract to each other, and the force we can say at our home also. That is, in your home there is a two conductors or two wires which are near to each other, and the current in the two wire is same. Then these two wires will attract to each other, and this force is very small. Therefore, we must observe it very carefully. Very small force is exerted here. Now, we will discuss about the wires or currents. If the currents in the wire is in the opposite direction, wire is in opposite direction, or we can say that the current is anti-parallel. Suppose this is current I1 and this is current I2. This is wire first, this is wire second. Here the current in the wire first I1 and I2 is the current in the wire second. The direction of current is changed here. Therefore, the direction of force also be changed, and D is the distance between these two wires. Then the force on the wire second will be in this direction, that is F21, and force on the wire will be in this direction, that is F12. Force on wire first due to the current in the wire second, and this is the force on the wire second due to current in the wire first. These two we can find out by using the right hand rule. Here we can also apply the right hand rule here to find the direction of force. Now what will be the how can we apply this forefinger pointed in the direction of current and the middle finger is pointed in the direction of magnetic force. Then we can find that the force is outward direction here, and this is also the away from the wire second. Therefore, these two forces are opposite to each other. These two forces are opposite to each other. That is, these two forces will repel to each other. There will be the repulsion in between these two wires. In the first case, if current is parallel, then the two wires attracts to each other, and if current is in the opposite direction or in anti-parallel, then these two wires repels to each other. There is a repulsion in between these two forces, and magnitude of force can be found out as same method. And the force, magnitude of force F12 is equal to F21, and the direction is opposite. Therefore, there will be the negative sign. That is, from this equation we can say that parallel currents attracts. Parallel current attracts and anti-parallel current repel. Parallel current attracts and anti-parallel current repel. Okay, now we will discuss about the unit of current. Unit of current. We know that the unit of current is ampere. Then what is mean of ampere, or what is the definition of ampere? That is, we can find here 1 ampere. 1 ampere means, or what is mean of 1 ampere? Or if there is a question, define ampere, define 1 ampere. Then how can we define the ampere here? Suppose 2 wires carrying current I1 and I2. 2 wires having current I1 and I2. I1 is the current in first wire, I2 is the current in second wire. These 2 wires are separated by distance D. Now we know that suppose these two wires are infinite long. The length of two wires is infinite here. And the formula of force per unit length we have discussed here. The force per unit length, that is F upon L, is given by equation mu naught upon 2 pi I1 I2 upon D. This equation also can be written by mu naught upon 4 pi. 2 pi instead of 2 pi we have taken here 4 pi to put the value of mu naught upon 4 pi. Then we can write here 2 I1 I2 divided by D. Force per unit length, that is mu naught upon 2 pi I1 to mu naught upon 4 pi to I1 I2 upon D. We have to find the value of 1 ampere, or we have to define the 1 ampere. Then if the current in the wire is unit, that is I1 is equal to I2 is equal to 1 ampere. Current in the wire, both wire, the current is same, that is I1 is equal to I2 is equal to 1 ampere. And distance between these two wires, a separation of these two wires is 1 meter. The distance between two wires is 1 meter. Put the value of this in this equation, then we get F upon L is equal to mu naught upon 4 pi. The value of mu naught upon 4 pi is 10 raised to minus 7 Tesla meter per ampere. Then mu naught upon 4 pi is equal to, we have already discussed this value, that is 10 raised to minus 7 into 2 as it is, into value of I1 1, then value of I2 is also 1, and then divided by the distance is 1. Therefore, the value of force per unit length will be 2 into 10 raised to minus 7 Newton per meter. Unit of force is Newton and unit of length is meter. Therefore, force per unit length is equal to 2 into 10 raised to minus 7 Newton per meter. From this, we can say that ampere is that current which when flows. Ampere is that current. Ampere is that current which when flow. We are going to find the definition of ampere. We have taken the current in ampere and the force per unit length is 2 into 10 raised to minus 7 Newton per meter. When we take the current in ampere, then force per unit length is equal to 2 into 10 raised to minus 7, and the distance between these two conductors is D. Therefore, we can say that the ampere is that current which flow when, or ampere is that current which when flow in two parallel infinite wires, in two parallel infinite wires which are kept 1 meter apart, and the force per is the force per unit length is 2 into 10 raised to minus 7 Newton per meter. The force per unit length is 2 into 10 raised to minus 7 Newton per meter length. Or we can say that force per unit length between them of 2 into 10 raised to minus 7 Newton per meter. Here 1 ampere current is taken and then we get the force of 2 into 10 raised to minus 7 and distance between these two wires is also 1 meter. Therefore 1 ampere is that current which when flow in two parallel infinite wire which are kept 1 meter apart and the force per unit length between them of 2 into 10 raised to minus 7 Newton per meter. This is the definition of 1 ampere. Okay. Now we will discuss the next point. Now let us find the magnetic field produced by a current in a circular arc of a wire. That is, magnetic field produced by a current in a circular arc of a wire. This is the circular arc, that is arc AB of a wire, and the current flowing through this wire is I, and we have to find out the magnetic field at the center of this circular arc. If we take as this is the circle and this will be the center of this circle, we have to find the magnetic field produced due to this circular arc. Here R is the radius of this circle, whose AB is the part of that circle or arc of that circle, and theta is the angle sustained by this arc. Theta is angle sustained by this arc AB at the center of circle. I is the current passing through this circle. Then dB is the magnetic field produced due to this wire or circular arc. Now we can find the direction of magnetic field produced due to wire. We can apply here the right hand thumb rule. That is, this right hand thumb rule can be applied as that. Hold the conductor in the right hand, point the thumb in the direction of current. Then this is the direction of current. Then the magnetic field, which is inward direction. This is the direction of current. That is, thumb is pointed in the direction of current. Therefore, magnetic field at every point, the magnetic field will be inward direction. Therefore, the magnetic field at every point is inward direction due to the current in the arc. Now we know that the Biot-Savart law Consider a small length dl. This is the small length dl of this arc. Then magnetic field produced due to this small length dl or current passing in this small length dl is given by the dB. Magnetic field dB in the vector form, dB is equal to mu naught upon 4 pi I dl sin theta upon r cube. dl cross r upon r cube. in the vector form, we can write here the vector dv is equal to mu naught upon 4 pi I dl cross r upon r2. In the form of magnitude, we can write this mu naught upon 4 pi I dl r sin theta upon r cube. I dl into r sin theta upon r cube. This is the magnitude of dv. dv is equal to mu naught upon 4 pi I dl r sin theta upon r cube. Now we have to take the value of theta. Here theta will be, now we can say this is not theta. This theta is not this theta, but this theta is the angle between dl and r. Therefore, we can write here instead of theta, we can write here a 90 degree, because there will be confusion in this angle and this angle. We have denoted the angle theta at the center sustained by this arc, but we are taking theta. This is the not this theta, but this is the angle theta here. That is angle between dl and the r. R is the distance of point where we have to find the magnetic field, and the length element. Length element is this, and the r is the radius of circular path, and the angle between these is 90 degree. Always when we take the circle and when we draw a line from the circumference of the circle to the center, then this angle is always 90 degree. From any point, if we draw the line from this circle or circumference, or we can take this small length of this circumference and the line from this small length to the center O, and the angle between this will be always 90. Therefore, this will be the angle between dl and r. Therefore, it will be 90 degree. And we know that sin 90 is equal to 1. Therefore, this dv is equal to mu naught upon 4 pi I dl upon r square. dv is equal to mu naught upon 4 pi I dl upon r square. This r and one of this r will be cancelled. Therefore, there will be the r square. Mu naught upon 4 pi I dl upon r square sin 90 is equal to 1. This is the magnetic field due to the small length. We have to find the magnetic field due to this whole arc. Therefore, we can take the integration of this. Therefore, taking the integration of this equation to find the total magnetic field. Therefore, the total magnetic field is equal to integration of dv, and this integration of dv is equal to this mu naught upon 4 pi can be taken outside. I also can taken outside, and integration will be dl upon r square, and the length of dl from a to b, or 0 to ab, we can say the limit as taken will be a to b, we can say, or this a to b limit can be taken as a to b dl upon r square. Now we know that dl is the arc length. Mechanical formula of dl is equal to, that is arc length is equal to radius into angle sustained by that length. Here dl is the small length, and therefore the angle sustained by this small length will be taken as d theta. Therefore r into d theta. Therefore we can write here mu naught upon 4 pi r d theta upon r square. Then limit will be changed here from 0 to theta. This will be a limit 0 to theta. Then this r will be cancelled and we can take outside, that is this will be 4 pi r. Then integration of d theta, and integration of d theta is equal to theta. The angle is maximum angle is sustained by AB is equal to theta. Therefore integration of d theta will be equal to theta mu naught I from 4 pi r into theta. And this is the magnetic field due to the arc length AD, that is mu naught upon 4 pi I upon r into theta. If we take the whole circle, then that is we can take as this type of whole circle. Then theta will be equal to this, or theta will be equal to 2 pi, because for the whole circle the angle will equal to 2 pi. Therefore we can put the value b is equal to mu naught I upon 4 pi r. Theta is equal to 2 pi. Therefore b is equal to mu naught I upon 2 pi. This is the magnetic field at the center of circular coil. That is b is equal to mu naught I upon 2 pi. Okay.